My name is Naresh Menon, and I am Director of Product Management within Imagination Technologies. My primary responsibility is to overlook product management activities for our RISC-V CPUs. Today's presentation is RISC-V for automotive heterogeneous compute. So I will be giving key insights into what are the challenges the automotive industry is currently going through, why tackling compute is now more so important than ever, and how RISC-V is contributing to the present and the shaping of the future of compute in automotive. The automotive industry is going through some of its biggest challenges at recent times. The key factors contributing to this is move to electrification because of the aspiration of having a greener planet, the quest for autonomy to ensure safe driving and also safety for passengers. Currently, there is level 2, level 2 plus in terms of autonomy, which is currently in the market, and there's a lot of innovation going in the level 4 space, like robotaxis. There is a change required in terms of the approach, and the time is right now. These key factors are also changing and triggering the change in terms of the vehicle architecture, in terms of change from distributed ECU architecture to a zonal architecture where the vehicle is divided into multiple zones and controlled by a central compute system. As the autonomy level increases, the compute requirements is comparable to a data center. Looking at all this, compute is a very important problem or a challenge in the automotive industry. And this is something we have to look at right now. So there are a lot of key trends which the OEMs use to enable differentiation, which is number of ICs, number of screens, and compute. But the thing which is underlining all of this is electronics, which is the turbocharger. The compute requirements is pushed further because of the advent of ADAS applications and AV. The requirement of compute is in tens of GOPS or to tens of TOPS in the ADAS applications. And in the autonomous vehicle side, it goes up to thousands of TOPS at level 4. Compute requirements are a right size fit approach we need to take, where the compute should be aligned to what kind of requirement is there for that particular application. RISC-V community can help with this kind of scalable market requirements for compute in automotive. As the advent of autonomy increases, the kind of data we need to process and the kind of algorithms we need to use is quite comprehensive and quite complex. And this trend is going to continue for the next 10 to 20 years. It's not only throwing high performance at every problem statement, but it's also trying to find the right compute solution for the architecture which is being currently considered. And also, all of this high performance also should tailor in tight power requirements, because this will drive battery range and also this will reduce the electricity consumed, leading to a greener planet. So now I have gone through all regards to about compute, but there are challenges. And I would list out a few of these challenges. The first one being the explosion of data. There's a lot of data in and around, and there's a lot of compute needed to be done on that data. But that compute is also increasingly diverse and complex. Scaling one single architecture cannot meet these challenges. So there is a change of approach required, and that is where we call in heterogeneous compute. In imagination, we've defined heterogeneous compute as the execution of tasks on a set of discrete compute architectures, enabling specific operations to be computed in the most efficient manner. The three key terms which I would like you to look at is discrete compute architectures. You can take CPUs, GPUs, ISPs, or you could take FFAs, which is the fixed function accelerators, and then enabling specific operations. So specific workloads tailored for each of those architectures coming together. But also we should consider efficiency. It's performance per power, performance per watt. So here is an example of a heterogeneous architecture where it is tailored to an autonomous vehicle system. This is divided into 5 stages. The first stage from the left is sensing. The different sensors which I have listed out are cameras. Examples of them are cameras, LiDAR, radar, ultrasonics, and all of them predominantly use a RISC-V CPU or DSP compute. The next one is the perceive and localize, where the kind of algorithms are object detection, lane detection, semantic segmentation, SLAM, and 70% of this is all AI ML accelerator based. As we move down, we see the scene representation where sensor fusion, behavioral prediction, object map is kind of coming to the forefront, and this requires parallel computing and hence a GPU in terms of a GPU compute and high performance threading kind of architecture on the CPU would be very beneficial. When we go to the plan and design phase, where there's a path and motion planning, trajectory, optimization, and driving policy, a blend of high performance and kind of some level of efficient CPUs are truly useful there. And the final, which is the control, where the actuation is happening of electrical power steering or acceleration and braking. A real-time RISC-V CPU would be very, very essential there, because you want determinism, you want quick response. So compute, I would say, is one size does not fit all, because you could have compute with a single element like a CPU cluster, and as the level of compute increases, you have that increase in level of heterogeneity coming into forefront, where you could have a CPU cluster with a fixed function accelerator, and at the right all the way you could have a complete compute subsystem. But the key thing to note is that RISC-V is enabling each of these kind of compute elements by giving us access to all of these fundamental extensions which are required for this, which is the I extension for the fixed function. You have the you have the single and double precision floating point for floating point arithmetic, and you have the vector extension which was ratified last year at this summit, just before this summit, for complex arithmetic in both fixed and floating point. So I touched upon hardware, But hardware is not only the thing which we need to consider. We need to consider software as well. I've drawn on the left-hand side a typical kind of a software environment we would expect in a compute in a compute environment. So I would like to divide this into like three kind of categories, where you have the tools at the end, the tools and the compilers, and then you have the libraries, which are the low and the high and the cross-functional type of libraries, and then you have the system application, which is using standard APIs. All of this is enabled by the huge ecosystem we have in RISC-V, but there needs to be a lot more work to be done there. The future of the software architecture is also changing in terms of currently it's a software enabled car where you can run cars using software, but the future is a software defined vehicle where the car's hardware is being enabled by over the air secure updates. RISC-V community has a lot of work which can be done to enrich and strengthen our ecosystem. So this was all what are the kind of things which are currently happening, but what are the future areas which we could think of in a heterogeneous kind of compute solution? So I divided that into three areas. Technology, the first one, accelerating ratification of compute enabling extensions like bfloat16, FP8. On the system side, you have the IOPMP, you have the IOMMU, and the second one could be innovating new accelerator extensions, optimizing software, helping with better libraries, better compute libraries. The second area I would highlight is safety, providing a robust platform to help conformance to the ISR. So when you go for a functional safety assessment, you have tests, or you have conformance to the architecture being validated and showing to an assessor. The other key things is trying to build new safety extensions and also safety focused extensions, and also looking at working together at the ecosystem to build new innovation in safety techniques. The third area is security, which is attestation, trusted device assignment, which is the TDSP, CXL integration. You have the finer grained isolation, and you have the cryptographic memory isolation. So there's a call for action here, and all of these challenges should be discussed in some forum. And Imagination has just initiated the Automotive Special Interest Group. This group is a place where all of these kind of discussions can take place and can work towards the right solutions or the right kind of trends in the automotive sector from RISC-V world. Currently, the Automotive Special Interest Group is looking at baselining the activities, where it is currently looking at whether the RISC-V ISA does match the market requirements, how to accelerate the adoption of RISC-V, and also looking at how we can enable ecosystem, and also figuring out how strong the ecosystem are in certain areas and what are the areas we need to improve. Once this is baselined, we will reach out to key members in the ecosystem to provide some sort of investment within the special interest group in terms of people to look at the trends in the market, and to define innovation in terms of techniques and solutions to help RISC-V be in the bleeding edge of this technology. The special interest group also will help in broadening and building up the strong relationship required, which will help build the RISC-V CPU, RISC-V compute, automotive story, and shape this for the better future. So I would like to conclude that RISC-V is doing a lot of things for compute already by enabling a lot of these extensions. But there's miles to go before RISC-V sleeps in making this architecture the #1 architecture for compute in automotive. Thank you, everyone.